hydrostatic. It's not creating a wave-induced force, not wave-related, it just drives our buoyancy. That's it. Okay, so we don't need that bit. Let's drop that bit. So this is our dynamic pressure. So what does that do with depth? We've got the same function which we've just looked at, how it affects the depth variation of velocity, and we've seen that velocity reduces from 0.55 at the surface to 0.26 to 0.1, and pressure's following the same function. So it's again decaying with depth. Right, so the first part then is sketch depth variation of dynamic pressure. So we've got something like that. Probably not even that curved. Let's make it slightly less curved. Right, like that then. Okay, and as we keep going down, if it's in infinitely deep water, this will go to 0, and if it's in intermediate water, it'll just be less at the bed, but not necessarily 0 at the bed. Okay, so this is going to vary, obviously, because we've got a cos term at the end. Cos kx minus omega t. Right, so that tells us that when the cos term is 1, our dynamic pressure is maximum, and our cos term is 1 when we're underneath a wave crest. So we would have this distribution positive if we had a wave crest at this point. This is an exaggerated vertical scale. Right? I'm just going to move that label onto the other side so we've got a bit more space. Right, so if we're underneath a wave crest, we could write that there, and we'd have maximum pressure, because the cos term is equal to 1. If, conversely, we're underneath a wave trough, which would be maybe a dashed line, get rid of our hydrostatic pressure because we don't need that. Right, we could have, we would have exactly the same distribution, but negative. Right, so this is underneath a trough. So at any point in the fluid, and it's only varying with depth at the moment, we can obtain our magnitude of dynamic pressure. Okay, and in the notes we looked at getting the vertical force on an arbitrary geometry. We had a 5 metre wide block, I think. So we evaluated the pressure at a point here on the base of the float, right, and got the pressure acting upwards there, and then we could integrate that pressure across this width as a uniformly distributed load across the base, say, because it's quite a small structure, right, and therefore give a force. So F3 is just width, whatever you want to call that, yeah, so just WF3, times pressure at Z is equal to -6. Right? So that would be, so F3 is upwards, so that would be that. So if we were going in that direction. Okay, so that's what we've done in the notes. Yep. Which you should be happy with an example with a 5-second wave and a 8-second wave, maybe? 2 different wave periods, anyway, for a given depth, and a 5 metre wide block. So let's do the same then for the third direction. Okay? Oh, well, I suppose one other point there. So this pressure is purely from that equation. So if you recall, we had a little animation. If we do that, right, we're allowing water to pass through that surface still, through all of the surfaces of the body. Okay, so we're calculating stuff on the boundary, pressures on the boundary, but we're assuming that the boundary isn't affecting the flow in any way. Right, so we can still allow velocities through it, which is slightly dubious, you might think, but it's actually a reasonably good approximation. Okay, so the first part of this question, we've probably got about as far as now, says something about sketch pressure distribution. Is that the one? Sketch pressure distribution on both sides. Sketch depth variation of dynamic pressure on the vertical surface of the plate. Alright, so that's just this, really. We could just translate that structure into this bit here. So let's draw our structure in this gap now. Right? And it's got this pressure acting along that line. Right, so on this side, it's got, well, underneath a wave crest, it's got this distribution on this side, so if we draw the centre line, right, so that's that centre line, and we've got this pressure distribution acting on the side, right, and we're underneath, say, a wave crest up here. exaggerated scale. Okay, so we've got pressure acting inwards on this side, because pressure acts normal to a surface. Right, and on the other side, because we're underneath a wave trough, underneath a wave trough, 180 degrees there, underneath a wave crest, we've got exactly the same pressure distribution, not negative yet, right, and it's still acting inwards on the structure. Right, so at that point, underneath a wave crest, this force this pressure distribution is exactly the same as this pressure distribution, and it's cancelling out. Gravity. So that's not the answer to the question. Right? But we're partway there. We've got the shape of the pressure distribution, we just haven't necessarily got the right point in the wave cycle. Okay, so think through then what happens as we move through a wave cycle. Here we're at a crest, so we've got the maximum, this distance is as maximum as it can be, the surface elevations. We've got maximum pressure going this way and maximum pressure going that way, both acting normally. It's the same pressure but acting in different directions because the surface is the other way around. Alright, so if we then think through the wave cycle, this same profile applies at any point. All that changes is the sign of these arrows. Yeah, so if we're underneath a wave crest, we've got the arrows going inwards because we've got a positive pressure on the surface here to sustain this surface here. If, conversely, the surface is reduced and we've got a trough, right, then all of the points around the surface must be pulling down to that point. So we must have suction on these surfaces to pull that point down. Right, so these pressures are now then acting outwards if we're underneath a wave trough. They just have the same distribution, but the sign and the magnitude have changed. Okay, so at what point in the wave cycle? So again, if we're underneath a trough, right, we've got equal pressures on both sides around this centre line. Yep, and they still just cancel out only around that centre line itself. Right, so what we want is a point in the wave cycle at which the forces or the pressures are combining to give us the maximum net force on the structure. So how do we get how do these pressure distributions ever combine to give us a maximum, or to give us a net force sideways on the structure? So we've looked at crest and trough. What happens in between the two? Okay, well, let's put a wave cycle. We'll give these up and a new one. So if we have a wave cycle as thus, we've looked at this point, we've looked at that point. This is the long run mean. Actually, that's a poor way to draw a wave cycle, so we've got a cost function, so let's start there instead. Right. So that's one wave period. T is equal to, what's our wave period? 12 seconds. T is equal to 12 seconds. Right, and that's T is equal to 0 seconds. So at what point in, and we looked at here, and we looked at here, I did the same, that's just a repeat cycle. Okay, so what does the pressure distribution do in between? So here we've got pressures with these profiles acting onto the surface of our structure. Here we've got negative pressures with the same profile and they're both acting outwards from the structure. Right? So at some point in between they change sign, so either here or here. Right? So for a very small amount of time we're going to have a small pressure distribution, but there's going to be a difference between the two. So at this point, for example, here, if we have our structure sketched beneath again, we're going to have, if we look slightly to the left of the structure, we're going to have a positive surface elevation, and slightly to the right, we're going to have a negative surface elevation. So that's plus, and that's minus. Right, so on the left-hand side of our structure, we've got onwards pressure, right, because the surface is doing, to draw it at an exaggerated scale, our surface is doing that. Okay, so on the left-hand side we've got that, and on the right-hand side we've got suction, because the surface is pulled down at this point. points close to zero crossings then, we've got a similar pressure distribution calculated in, well, a similar shape to the pressure distribution, but we've got a net force sideways just because of the extent of the device, this formulated width of the device. So from this point on the surface to this point on the surface, we've got a pressure difference, and that's giving us a net force in one direction. Okay? So we don't really need then that one, because that's not part of the question, that's just what we've already done for F3, which is what we're nearly always more interested in for F3. Right, so that gives us a point in the wave cycle where we can start our calculation. So this point then occurs where? This occurs at t is equal to 6 seconds, which is t on 2, obviously. So this occurs at 3 seconds and, in this instance, 9 seconds. So you choose either, doesn't really matter. And evaluate then the pressure on one side. Okay, so that would be F3, so we could then write equivalent for F1 is equal to, let's call this a graph, H equals, right, H, well, that's a bit overly long, we should write really, integral of this from Z is equal to minus 8 to naught of P Z B Z. That's a bit of fab. So what we want to do is get the pressure, integrate this pressure then over this distance to get a net force on our side of our structure. Right, so this is just saying integration, and this is what's given in the geometry solution. Z is equal to minus h, which is here. Z is equal to naught, which is here. Right, so how are we going to do that? How do we then obtain these values? Okay, well, we're going to go back to our equation and plug in terms of that. I think how we're going to evaluate that first. So this is decaying, but we could make an approximation to it if we wanted. Maybe say it does something like that. Once we've evaluated some values, we see that it does do something like that. And it all becomes a lot simpler to evaluate the force. So what we actually need is the pressure either here and here, and take the average, or just directly the pressure here, which is what I've given in the solution. Okay, so if we get the pressure there, we could write this formula approximately as H times P of Z is equal to minus H on 2, i.e. 6 times P equals minus 3. Okay, so all we want then to evaluate all of this expression is the pressure at a given point on the surface. At a given point in the wave cycle that we've thought through, that is going to give us the maximum combined force on the structure. So at that point, so this point then is Z is equal to minus 3 meters, and X is equal to minus 2 meters. Right, with our point in the wave period being 3 seconds, so we should add that. So T equals 3 seconds or 9, let's do 9 because that's what we need in the exam, and then we've got the numbers to refer back to. Right, doesn't really matter. If we do it at 3, we're going to get a positive value. If we do it at 9, we're going to get a negative value. But it doesn't matter. So we're evaluating our pressure then, our dynamic pressure, with those 3 inputs to get pressure at that point, and then plug into this equation to get force in that direction. So F1 is approximately that.
30. How did you get x is 2 or minus 2?
So that's just from the width of our structure.
Oh, right.
Yeah, so in our first conceptual drawing we were saying we're looking at the pressure around a single centre line, and that's there. Okay? But if we do that, if we only look at a zero width structure, we're still going to get the same pressure on both sides because we're looking at the same point in space. So if we looked at there, yeah, we'd still get pressure that way is exactly the same as pressure that way because it's cancelling out. Right? But if we look at points that are very slightly separated in space, we're going to get a net force. Is that another question?
Just to confirm, you're measuring from the centre and you're going left, clockwise minus 2.
Yeah.
Yeah.
Yeah. So if we evaluate that, we've then got our dynamic pressure then as a function of 3 variables, which is what I write in the notes here. We've got Z. Z is the dominant one, so not the right first, right in order of appearance. This will give you what you want. Equals our rho GH over 2. I think we've got unit amplitude here, haven't we? H over 2, and then our cosh K Z plus D. Is this finite depth? It is finite depth. K would be evaluated in the same way as previous. K Z plus D, so minus 3 plus 30. Over 30. And we've got cos K 2 is under 9. Okay, so that's our first point. Which one up there? Right, so any values? So we can simplify because we're assuming a unit amplitude, so this bit just falls out because so that bit's gone, so we've just got that.
Is A1?
A is, well, yeah, unit amplitude. Okay, so I haven't got it written down at the moment. So K and omega, so here we're getting those from omega squared, well, let's do it later. K is equal to omega squared G term D. Right, omega is 2 pi over 12, so it's not very much.
You get from 2 pi over L, then you literally have a flat function. You know that you just keep it. Well, you couldn't do that many marks. I don't think if you did. If you rushed it. Just to shoot
Yes,
whatever.
first one,
Okay.
say, times 30. And then iterate.
So is that what you said last time? You have to yeah. You can't keep it though from like in the last one. I think you kept it just to do it quicker. But you're supposed to iterate it.
So we need that and we need that.
It's not that long, I'm just lazy.
Same here, that's why I copied it.
So, right, we've got, gosh, point.
What are you at, KDB?
No, 3, 5, 5. Not 3, 5, 5.
And then we've got our cos term from rapids. Right, and we'll get any number split when you plug it in. Probably best not to plug that all into your calculator window. You calculate as much. So I get that as 9269. So that would be just this first part without the time variable part. So that's what would happen underneath a wave crest on its own. Alright, so we've so far just done that first bit. So that's whatever, newtons per metre squared if cos equals 1. But it doesn't. So the cos term then equals something else. So we've actually got 9269 times cos of all that bit. 0.0355 minus 2 minus 0.524 times 9 equals 9269. We don't really need to be this precise, I'm sure, but times 0.106. Right, we expect this to be quite small because we're only at this point in the wave cycle, which is a little way from the zero crossing. Right, equals then 984 newtons per metre squared. So at that point,
No, answer that question.
in the fluid, where the surface of the structure would be if the structure was there, but it isn't. We have a pressure of 984 newtons per metre squared acting onto that 6 metre high and 10 metre wide wall. We could do the same calculation on the other side, but there's not really much point because we only need the pressure at the mirror image point. Right, so we've got the same amplitude pressure that's fluctuating, and we're just at a different point in the cycle. So we just look with our -2 point in the wave cycle, so same instant in the wave cycle, but a few metres further forward, 4 metres further forward, this side of the structure instead, i.e. this point down here. Okay, so that's just going to be minus that. So on this side we've got onwards 984 newtons per metre squared, and on this side we've got outwards, here we can 984, and here we've got minus 984. But because it's minus, it's just telling us it's actually out, so we can account for the minus by the arrow. So that's 984, and that is also then 984 going out.
Pretty sure I picked the other part of the
984 out.
Pretty sure when you chose 9 seconds, I picked the other part of it. Pretty sure the signs were supposed to be reversed. Wait. Do you know what I'm saying?
Alright, so once we've got that, it should be quite straightforward to get force because we just take our pressure and multiply it by 6 by 10, I guess, because that's the width of the structure.
Positive should be on the right hand, should be an x equals 2. Yeah. Yeah. Because the suction should be on the trough side, isn't it? Should be the left hand side. Down.
If you pick the 9-second point, shouldn't the signs be shouldn't it be coming out on the left hand side and going in on the right hand side?
Yeah, sorry, I'm drawing my diagram for the 20-second points.
Okay.
Yeah, but we've calculated the other side. So what we've just calculated is actually the other side.
Okay.
So, very good. But yeah, I'll keep the diagram straight to screen again. Alright, so that's the 3-second point. Alright, so
Just if you draw the right.
but we're interested in the amplitude anyway, so
Yeah.
just get rid of the signs. Okay, so we have the net pressure acting on our centre line then is just this plus this, because that's on and that's off. Right, and then multiplied by 6 and multiplied by 10.
How would your pressure stay the same though if you're multiplying by 9? The other time if you multiply by 10.
Yep.
We've got something different in your solution for the cost term.
He's finding
But
both
it has
of them. He's just changing the
0.0709.
Because I was asking the
So
question.
the force comes out to
He's just changing the x's.
67.
What does it say?
Why? For the same input.
Yeah, I've put in my calculator, I get some.
So this
I
you
get
can-
some
this you can use
It
it.
doesn't ask you to use it, but you can put it through
Yeah,
your
you can use it 3, but
So
different.
for both of
yeah,
them,
so
use
you get a
3.
force of 6,
Yeah, yeah.
57 newtons per metre squared.
57.
657.
657. Okay, so same process. So what's different there? Same K
Um,
and same O?
The numbers are the same in the solutions as well, but you just get a different answer. I put in my calculator, you get 0.0745.
So process the same difference. So what are you getting? 5?
Yeah, so for the answer you get 657 newtons per metre squared. That's from your solutions.
It's the constant.
Yeah.
Are you using a 9 or a 3?
It's 9. I think it's the cos term that's worked out wrong.
Yeah.
Okay, so there's a number plugged in wrong in that one.
Yeah, it should.
So that should be 0.07.
Yeah. That should be
So let's
0.07.
get used to 3, so maybe that should be 3. So you're saying that's 0.079.
Yeah.
Right. Okay, and then you get 687 or
Yeah.
687?
It's 0.071. It's 0.0709.
And 687.
657.